So how do we deal with strength on the periodic chart? So there are some nice ways to look at this that make some of it easier. And you can think of them in terms of overall trends. The explanations in here are explanations for why the trend is what it is. But you can also just learn the trend. So the strong acids are found in this part of the periodic chart. So you're going to be going over and you're also going to be going up to be a strong acid. I like to summarize it in one arrow going in that direction. The binary acids, they're strong on kind of the bottom right. So this is an unusual spot on the periodic chart for something to be big or strong. It's usually like here or over here. But not so with the binaries. And so these ones still increase going across. They still go that direction, but these one increase going down. So the overall trend for those ones is to go in that direction. So why does it do this? So here's our whys. The first ones are when we're going left to right in a row. You can see that they both go left to right. They both increase left to right in acidity. Oh, and in case you had forgotten, binary acids are things that have an H and one other element, like H2S or like HF. Those are binary. Strong oxo acids would be something that has some oxygen in it, like HSO3, HNO2. These are weak acid forms. They do have similar formulas that are strong, but these are not the strong formulas. These are the weak ones. But that's the difference in the two. But both of them increase left to right. And it's because the electronegativity increases when you go in this directions. And so what that does when you're looking at a bond, and this is for both cases, when you're talking about where the electrons in this bond, there are two, where they want to play, they like fluorine better. So they are closer to fluorine in their electronegativity. They like that one more. And if the electrons are already all hanging out over here, then it just makes it easier for the H to pop off. Versus something that's more on this side, like the carbon, it doesn't do good acid anything at all, because although it's close to the carbon, it's nowhere near as close. This is going to be like a 2.5 and this is 2.1. There's hardly any difference in the two of them, versus this is 4 and 2.1. Big difference. They're all like fluorine cells. In here, they're mostly in the middle. So that H won't just drop off of a hydrogen. It just don't like to leave hydrogens. Not like that. So it's the electronegativity, and it's true for both of them. The electronegativity as you go across the chart gets stronger and stronger, which means the electrons are being held by the other element, which makes it easy for the H to pop off. So then as a contrast, we can say that the trend increases downwards for binary acids, but upwards for oxo acids. So here's our down for binaries and up for oxos. So they have different reasons. One is because for the binary, that central atom, the one that isn't the H, as you go down, you get really big. So maybe you start here, and then you get here, and then you get here. A hydrogen is really tiny comparatively. And when it gets this small, it's really easy because it can't contact as much as the atom. It's really easy to just drop that hydrogen off. So again, it has to do with, it just can't hold onto it very easily because all of its electrons are all over the place. Even here, it's going to be hard to hold on to it, but at least there's more electrons that might be nearby that hydrogen. So when you go down, it has to do with the size. The size makes it easy for the little H to pop off, the bigger it is. The reason that the oxo acids don't do it is because it's the electronegativity of the other element. So this is related to when you have an O before you get to the H. So this is how these guys look. You don't really realize that they look like that. But what happens is that the more electronegative this one is, the more those electrons are kind of going in that direction. It also kind of affects the oxygen, and its electrons are kind of going in that direction too. So when they both are going in that direction, it means that there's not much left to hold on to that hydrogen, and it falls off. And additionally, this element here, as this one's pushing in, this one's also kind of pushing in, and this one's also pushing in. And if they're kind of pushing in, it also means that their electrons can kind of jump around. So we're going to talk about what those electrons are doing right there. And it's a special case just for the oxo acids. But if you're an oxo acid, the more oxygens that you have, see how that has more? It has 4 versus 2. The more oxygen you have, the more those electrons can spread their charge around and exist on their own. So we have H's here, and say the rest isn't an H. Then these oxygens right here, some of them are singles and some of them are not. And so they can be in resonance, and like this one can like jump over there, and then these ones can jump back over here, or it can jump down that way and go back up, but they can move around. And the more resonance you have over here, the more stability, and the less that they need the hydrogen, which again lets it pop off, because they're fine being stable and not needing that H. So more oxygens do that. So I've got some examples of these. And we also have a little thing about base strength. So we'll look at what happens for the base strength. I'll just make a little note so that you have it written down. The stronger the acid, meaning it wants to give up that H, the weaker the base. And the reverse is true also. The weaker the acid, meaning it kind of wants to hold on to its H. It kind of sort of will give it up, kind of, but it doesn't really want to. That's being a strong base, because remember, it's base accept electrons. So if they kind of want to hold on to their H, the base side of it is like accepting it, and it's happy like that. So let's just show some examples so that you're kind of clear on it. So we're going to circle the stronger in each pair. So we're going to look at binary acid, oxo acids, and then the oxygen, and then we'll compare it with the base strength. So the first thing is, between these two elements, which one is going to be the stronger acid? So here's I. So when I'm coloring it, I'm doing the I because I have an I right there. And then here's my Cl, and I have a Cl right there. So here's the trend for binary acids. So the trend is that the further one down, the better the acid. And so you can see that that's why I've got this one circled right here, because this one is further down. This is the stronger acid of that set. Now in contrast, I'm going to color this hot chlorine right there, and we're going to look at the bromine. So here's my bromine right here. So we're going to look at those two. Now the strong oxo acid trend, this one is saying that you need to go up to get your strong oxo acid. So that's why I have this one circled. So that's tricky, right? You've got to keep it straight. If you've an oxo acid, it's upwards is stronger. If you're a regular old acid with no oxygens, downwards is stronger. And then here's this one, the oxo acid strength. So if I'm comparing 4 oxygens to 3, as long as I've got the same element in the middle, the 4 is going to be the better one. And you'll notice that if this is my strongest acid, and we're comparing the base form, the form that's missing the H, that would mean that this is my weakest base. If this is my weaker acid, then that means that this is my strongest base. And again, so you can see I've chosen the opposite one for the base strength. And here's this one's opposite one for the base strength. So if you want to pause it and you can try, make sure you've got them right, and then you'll be good to go. And that's the end of this section. I'll mark them, but go ahead and pause it. This one's set up to be tricky because you're supposed to first look at it and be like, well, one's like, you know, a step away and one's a step away each direction. It takes a minute. You want to think about it. What do you know is the list of strong acids? HCl, HBr, HIO. Look, HCl is a strong acid. It's in my strong acid list. We know HCl is a strong acid, especially compared to water. We can drink water. We can't drink HCl. So that's a case where, like, you also need to remember that there is just a strong option. So now I've got the opposite ones here that I will circle for the bases, So this one, and this one.